Alright, so this video is on material from section 4.4 in the textbook for Math 1560, Calculus 1 at U of L for fall 2017. And in this video we're going to take a brief look at linear approximations. Now this is a topic we've seen before, right? This is something we discussed when we first looked at the derivative, and so you'll remember that when we set up the definition of the derivative, you'll remember where this definition comes from. You have the graph of some function, and you're interested in determining the equation of the tangent line at some point. Let's say we're interested in the tangent line at this point here, right? So that's your a value. And we said that, well, the way you calculate this derivative, is the derivative is the slope of the tangent line, and the way that you find the tangent line is you consider this sequence of secant lines where you choose 2 points on the curve, right? You choose a second point that's nearby, so you choose some other point there, and you draw the line between those two, right? So we draw this line and we say, well, that's not quite good enough, so you move the line a little bit closer and a little bit closer, and then finally, as those 2 points come together, you get this tangent line, this line that just touches, right? And we talked about the fact that if you were to zoom in on this area here and kind of expand, I don't know how well that works on here. I guess we can kind of do it here, right? If you zoom in, you'll notice that there's not a lot of daylight between the curve and the line. Of course, it's sort of hard to see there, so we might want to zoom out, kind of, not technologically, but just look at this piece of the curve. So the piece of the curve, kind of close up, looks like that. You got your point, it's here, and you draw your line, and you can see that they're pretty close together. And if you zoomed even further, you would see the curve would look like that, and the line would look like that, right? And the more you zoom, the less you can tell the difference between them. Okay, so that's kind of, we talked about that in the context of defining the derivative. We saw how to make sense of that, and so, and you can see this even just thinking about the definition of the derivative, right? So you get equality, we say that f prime is this limit. Remember what the limit means. It means that we can make the value of this difference quotient as close to the true slope of the tangent line, as close as we want, if we take h sufficiently close to 0, right? So when the h, which is basically our delta x, if that's sufficiently small, then f prime is approximately delta y over delta x, right? It's approximately rise over run. It's approximately the slope of one of those nearby secant lines. And so if you think about it, well, so delta y is, let's fix that, right? Not plus, but minus. It's the difference between f at those 2 points. Actually, let's see, I can probably, we can probably make that. Let's see. There we go. Turn my pen into an eraser. Size 6. There we go. There we go. See, there's ways of fixing things. Okay, so put that minus sign in. F of x minus f of a is your delta y. And so if you just multiply here by delta x, right, multiply both sides of this equation by delta x, then we see that, okay, f of a plus delta x minus f of a, well, that's approximately f prime of a times delta x. Okay, so in other words, if we look at a plus delta x, that's equal to f of a plus f prime of a times delta x. Okay. And then the other thing we could do here is we could say, well, for delta x equal to x minus a, so x then being, in some sense close to a, this becomes f of x is, and I guess really we should still say approximately here, right? F of x is approximately f of a plus f prime of a times x minus a. And so what you have on the left, right, these are going to give you y values for the original curve. And what does this expression on the right give you? Well, if you set that equal to y, what you get is exactly the equation of this tangent line. So this gives you y values for the tangent line, right? And so this, in some sense, formalizes this idea that the tangent line gives you this good approximation to the original graph, that y values on the tangent line are close to the y values on the original curve. And thinking in terms of functions, right, remember that f of a and f prime of a, those are just numbers. So the function on the right is a linear function. And we like linear functions when we can find them, because linear functions are much easier to work with than general functions, which can be much more complicated. Okay, so this leads to the following definition. So if we have a differentiable function, we say that the linearization of that function is this right-hand side, this approximation that we saw in the previous slide. So this is the linear approximation at a point, right? So of course this linear approximation doesn't work anywhere. It only works at a particular point. If we move to a different point, then we would have to change the values for f of a, for f prime of a, and of course for a, we would need a different linear function at a different point. But as long as we stick around, the neighborhood of that point, we don't move too far away, then this function, this linear function, is a good approximation for what we started with, right? And now these decorations I've put here, the f and the a, that's something that you might want if you were talking about linearizations for more than one function, or if you were considering a linearization at more than one point, then you might want to be able to distinguish between different functions or different points. If you're just looking for a linear approximation at a point, right, where the entire context is there's just a single function in a single point, then you probably want to just call that L of x and don't worry about the subscripts, right? So as we mentioned, this, if you set y equal to this thing, you set y equal to f of a plus f prime of a times x minus a, what you get is the equation of the tangent line through a particular point. Okay, so let's see how this works. Let's look at an example. All right. So, and then we're going to put this thing to use. So here's our function. It's a square root function. So not too complicated, but still, it's a little bit more complicated than a linear function, or really even a polynomial function. So how do we calculate this thing? So we have to calculate. So we know that L of f at 0, and we'll just call that L of x from now on, is given by f of 0 plus f prime of 0 times, well, x minus 0. So f of 0 we can calculate right away. That's the square root of 4 plus 0, which is 2. That's convenient, right? We have a perfect square under the square root, so that square root is easy to calculate. F prime of x is going to be, so remember that this is 4 plus x to the 1/2. So we do the power rule, 1/2, 4 plus x to the minus 1/2. Then we multiply by the derivative of 4 plus x, which is just 1. Okay, so we get 1 over 2 times the square root of 4 plus x, and that means that f prime at 0 is going to be 1 over 2 times the square root of 4, which is 1 over 2 times 2, so 1 over 4. That means that the linearization of my function is f of 0, which is 2, plus f prime of 0, 1/4, times x, right? Minus 0, but we don't need to write the minus 0. And again, just as a reminder, note that y equals 1/4 x plus 2 gives the tangent line to the equation y equals square root of 4 plus x at the point x equals 0, y equals 2. Okay, so keep that in mind. Now, what about the approximation here? So for the approximation, we use the fact that for x near 0, f of x is approximately L of x. And so we notice that the square root of 4.02, well, that's the square root of 4 plus 0.02. So this is our x value. That's pretty close to 0. So this is f of 0.02, and we can approximate that by L of 0.02. So we get 2 plus 1/4 of 0.02. And actually we can work out what that is. So multiplying by 1 over 4 means dividing by 4. Dividing by 4, we're dividing twice by 2. Right? So multiply by a half, that 0.02 becomes a 0.01. Multiply by a half again, I get 0.005. So I get 2.005. Right? And of course you could have done that in your calculator, but the point is that this is something that you could work out. This decimal here is something you can work out without the use of a calculator. Whereas if you were trying to get the exact value for that square root, well, you wouldn't have much choice. You'd have to go to the calculator. And actually, maybe just so we can get an idea, what is that actual square root? Let's see if we can do it. 4.02, and let's take the square root. 2.00499, and then some others. So I would say that our linear approximation of 2.005 is pretty darn good in this case, right? So this is why we like linear approximations. They're easier to calculate than the precise value, and in a lot of cases they're almost as accurate. Okay, so that's it for this video. In the next video we will talk about differentials.